So, we're going to start off by talking about particle physics, or understanding the atom. Particle physics can be broken up into two subcategories, quantum mechanics and nuclear physics. Starting with quantum mechanics is basically the wave nature of particles. We can also think of it as the interaction between electromagnetic waves, which is like light and radiation, and little tiny particles, like electrons, for example. There are two key ideas to focus on in terms of quantum mechanics. First one is the photoelectric effect, photo meaning light, electric meaning electrons, so the interaction between light and electrons, and then also the Bohr model of an atom, and going along with that, atomic spectra. So, starting with the photoelectric effect, what is it? Well, let's say we have a material. The material is made up of atoms, and atoms have electrons. If we shine light on those electrons, they can gain energy. And if they have enough energy, they can jump to different energy levels, or different orbits, if you will. If the energy level is low enough, the electron will just jump back down to a lower energy level, or lower orbit, and emit a different color of light to conserve energy. If the energy level is high enough, though, the electron will actually leave the material, in which we can use it to do work, or provide electricity. So here's some examples. It's not the only examples, but here are some examples of the photoelectric effect at work. LEDs, or diodes in general, this is a light-emitting diode. Basically, we're putting electrical energy in, and we get light out. Fireworks are another example. Here we're putting in like thermal energy in, and we get light and electrical energy out through sparks and stuff. Solar panels, we're putting light energy in, and we're getting electrical energy out. And X-rays, not to be confused with X-ray images, because that's different. That's the application of X-rays. But X-rays are basically when you put in thermal energy into an atom, and there's enough energy to actually remove the atom, and then the atom has high enough energy to produce electrical energy, or X-rays, which are really, really high energy light waves, or radiation. So basically we're putting in energy to remove an electron, or have it jump back down to produce radiation. So that's what X-rays are. The application of X-rays is using those to image things, because X-rays are very high energy, and so they can image things at very high quality. But this is talking about the actual X-ray itself, not the image. So all of these from above deal with the photoelectric effect, and the photoelectric effect is basically just conservation of energy. And we're dealing with these types of energy in particular: electrical energy, light energy, thermal energy, and ionization energy. So let's go step by step. Those four examples. For LEDs, electrical energy goes in, that electrical energy goes into ionization energy, plus light energy, plus thermal energy. So we're putting electricity in, and we have to ionize the material, and then it produces light, obviously, because there's lights, and there's a little bit of thermal energy left over because it does get a little warm. Fireworks, we put thermal energy in because it gets really hot. That energy goes into ionization energy, light energy because it produces lights, and then a little bit of electrical energy. Think about the sparks of the fireworks. Right? Solar panels, we're putting light energy in, like from the sun. That light energy goes into ionization energy to ionize the materials, and then electrical energy is left over, which we use to then power devices. And then for X-rays, thermal energy goes in, and then energy goes into ionization energy, light energy, and electrical energy. That light energy being radiation or X-rays. So what is ionization energy? We talked about it a little bit. It's also called work function. It's the minimum amount of energy needed to remove an electron from a material. The equation for it would be voltage times charge. Now, if you remember, voltage could be written as voltage equals kQ over R, where K is Coulomb's constant. Q would be the charge of the nucleus, and R would be the distance away from the nucleus. So if we multiply by charge, we get electrical energy is equal to KQQ over R. So ionization energy can be basically written down as K times Q over R, where K is Coulomb's constant. Big Q would be the charge of the nucleus, which depends on the number of protons. Little q would be the charge of the electron, which is just the elementary charge. And then r would be the radius away, the distance away from the nucleus. So the farther away you are from the nucleus, the easier it is to remove it. That's why the valence electrons are easier to remove than the electrons closer in. So let's go into the more in depth about the photoelectric effect. We talked about the photoelectric effect. One example is when we put light into a material and then it ionizes the material. Let's say this is a material, it ionizes it, and then that extra energy left over is electrical energy from the electrons. So case number one, let's say we put red light into this material. This is like a material of some sort. We put red light into it, and maybe some electrons might leave, but hardly any leave. And we can connect it to a battery or like some sort of charging device. And with this example, it doesn't really get much because red light is not very high energy. Versus blue light, which is a higher energy, it's a higher frequency, lower wavelength. We're going to get a much higher current. With this, we're going to get the electrons coming off much faster and much stronger, and much more energy, providing a lot more electrical energy with the blue light because we have more incoming light. So let's go through another example. Here is a little simulation which should kind of demonstrate that. First of all, let's turn the voltage down here and photoelectric effect lab. Let's say we have a wavelength of 550 nanometers, which is green light. Now, if you notice, there's no electrons being emitted from this potassium material. I'm shining some green light on it, and even if I make the green light really, really, really bright, no electrons are able to leave because this is not a high enough frequency or energy light. But if I would lower that wavelength to, let's say violet light, now we're noticing, hey, we're getting some electrons. And even if I go a little lower yet, let's say ultraviolet light, now we're getting a lot more electrons. So the higher energy light that we get, the more electrons leave. And you can see that the electrons are these little things that are leaving are electrons. The waves that are coming in are like photons of light, and then the little purple spheres that are leaving are electrons. And you can see there's lots of electrons detected, and the lower energy that we make this, the faster this is going to be. So the photoelectric effect can be written as an equation here. Light energy comes in this example, and it has to ionize the material. So ionization energy is going to be one of the output energies, plus electrical energy. Electrical energy is basically also known as kinetic energy of electrons, because if electrons have kinetic energy, they are moving, so they're providing electrical energy. So if I were to rewrite this equation, light energy coming in, that was the light that hit that material, equals ionization energy plus electrical energy, we can write it like this. Light energy is equal to HF equals, this is the symbol for ionization energy, plus electrical energy, which is basically just the charge of an electron times the voltage. If I rearrange this, I can get this equation, where E would be the charge of an electron, V would be the voltage, the maximum voltage that I can produce, H is Planck's constant, F is the frequency of light, and then minus the ionization energy because I subtracted off when I subtracted over. So one application of this are solar panels. Here's a circuit diagram of one example of a solar panel. This would be like a solar panel. Light comes in and hits the solar panel, and it produces a maximum voltage of 1.5. Using this equation, we can figure that out. This is just an example. The solar panel is like go through a diode, which then can charge a battery or a capacitor possibly. And then let's say we can have a switch over here or something. We can switch this capacitor or battery on, and it could power something like a motor or a resistor or some sort of device. Look, I got a notification from Pizza Hut. The next thing I want to talk about is the Bohr model of the atom and atomic spectra. So basically, this is part of a Bohr model of an atom. We have the nucleus here, first energy level, second energy level, third energy level, fourth and fifth. That's what the ends represent. Here we have electrons. So let's say we have an electron jumping from the fifth energy level down to the second energy level. That difference in orbits is associated with a certain amount of energy. And when that electron jumps down, basically it's reducing its energy and giving off light energy in return. And This jump is pretty big. That's a pretty big jump for energy. So that high energy produces an exact wavelength of 434 nanometer violet light. This electron that jumps from the fourth energy level to the second energy level emits a green light, which is a little bit higher energy, or like a bluish green light. This electron that jumps from the third energy level to the second energy level emits a red light, which is a lot higher energy. So this is an example of all the different things. Like, this is just 3 different jumps that electrons can make. It could start at 5 and jump down to 1, which would be the highest energy possible. It could start at 4 and jump down to 1, which would be a little bit lower energy. 3 down to 1, 2 down to 1. It could start at 3 and go to 2, which is an example. It could be at 4 and go down to 2. It could be at 4 and go down to 3. So there's actually lots of different examples here. There's actually 10 different jumps it could make, and each one of those jumps represents a different amount of energy, which would produce a different color on the spectra. Now, the cool thing about this atomic spectra is that every atom has its own energy levels. No two atoms are exactly the same. Each of these jumps is going to be different for each atom, so we can use it to identify things. So like beryllium, for example, is going to emit a certain wavelength of light of purple, and then like a violet blue, and then like a blue and a green. Copper is going to emit like these different colors. Manganese is going to emit these different colors. Strontium, titanium. So what we can do is we can use this to identify unknown materials, or things that are maybe shifted one way or another. Like the stars, for example. We can look at stars and know that they could be like what they're made out of, and if they're moving towards us or away from us using the Doppler effect. So that's kind of cool, because every atom has its own identity. It's like its DNA, if you will. Next, we'll talk about nuclear physics, which is the second part of particle physics. Basically, what we're going to do is talk about what's going to happen, what happens on the nucleus side of this. We talked about the different energy levels of electrons, but what's going on in the center? All right. So let's first go to fat building atoms, see what happens. So let's build a real basic atom here. We have hydrogen here. I'm going to add another positive charge here. We'll click on stability here. Right now it's unstable. Right now we want to get this neutralized. It's a helium atom. And so what I'm going to do is I'm going to add a neutron here. Now it becomes stable. Add another proton. It becomes unstable again. Add a neutron. It's still unstable. Add another neutron. It becomes stable. So now there's 3 neutrons, 3 protons. I'm going to add a proton here. Unstable. Neutron. Unstable. Neutron. Stable. So now there's 4 protons and 5 neutrons. All right? Now I have stable, stable again, carbon, 6 protons, and right now there's 5 stable again. So if you notice this, there has to be at least as many neutrons as there are protons. Let's talk about why that is. Well, what forces are at work here? Well, there's definitely electrostatic repulsion. The protons are both positively charged, and they are right next to each other. So they're going to repel each other with a lot of force. And then the other force that holds them together is a strong nuclear force. Now recall the electrostatic force is K times Q over R squared. Since R is very, very small, we're talking like 10 to the minus 15th meters here, and we're squaring it, that's going to make the electrostatic force tremendously huge, which means that there's a repulsion force of those protons that are going to try to push each other away with a tremendous amount of force. So the strong nuclear force holds them together. Well, here's what ends up happening. First we start with hydrogen. It was perfectly fine all by itself. But when we added that second proton in there, it became unstable. We needed to add some more neutrons to stabilize it. And then the same thing when we added lithium, the third proton. We need more neutrons here. And the cool thing is that small particles, what I mean by small is smaller than iron. Iron is the most stable nucleus there is. So everything's less large or smaller than iron is unstable because there aren't enough neutrons to hold the protons together. Neutrons provide the stability as that kind of holds the nucleus together. Now, if it becomes too big, then the particles become so far spread apart that they don't have that interaction anymore. So we're going to talk about why iron is the strongest nucleus and about nuclear stability. So where does this nuclear strength come from? Where does the nuclear force come from? Well, it comes from other particles called gluons. So let's imagine that this thing right here is like the nucleus. And these are like the particles, like the neutrons and the protons in the nucleus. Now there's more stuff than that than just neutrons or protons. We're going to talk in more detail about all the different particles that live inside the nucleus. But we can think of like gluons as like these tiny springs or forces that hold these things together. Now the cool thing is they can't act over large distances, but they're actually made up of other particles. And we're going to talk about what those other particles are for the gluons. So what are these other particles? Well, there are a lot of them. We're going to talk about a few of them with a little table here. All right, so what I did was I made a little table of all the different important particles. Now, these aren't the only particles, but these are the ones we're going to focus on. And this table says particle, what type of particle it is, what the mass of the particle is in kilograms, what the mass of the particle is in atomic mass units, which is another way to measure mass, what the charge of the particle is in elementary charges, and lepton number. We'll talk about what lepton number means in a second here too. So the first three particles we talked about were protons, neutrons, and electrons. Now they each have their own symbol too. Protons are usually represented by a P, neutrons are N, and electrons are E with a little negative sign next to it. Now the masses for these are very small, but they're not zero. So the mass of a proton is 1.67 times 10 to the minus 7 or 27 kilograms. Neutrons are about the same, just slightly heavier, very, very, very slightly heavier. And electrons are actually like 10,000 times smaller, if you notice, or not quite 10,000 times, but 10 to the fourth times smaller. As far as AMU goes, or unified atomic mass units, a proton is about 1, but it's not exactly 1. It's a little bit more than 1. It's 1.007, and a neutron is 1.008. An electron isn't 0, but it's close enough to 0 that we'll call it 0. Now, the charges of each of these, a lot of times we denote the charge of a proton as just plus 1, but in reality it's actually plus E. E represents the elementary charge, which is 1.6 times 10 to the minus 19th coulombs. And then an electron would be either negative 1 or negative E, more specifically. In terms of coulombs, it would be negative 1.6 times 10 to the minus 19th coulombs. And neutrons are neutral. Now, what does lepton number mean? Leptons represent, basically, is it a particle or is it an antiparticle? Particles and antiparticles, when they meet up, they basically annihilate each other. All particles have a lepton number of 1, and all antiparticles have a lepton number of negative 1. We'll talk about why that's important later. Now, protons and neutrons are not actually elementary particles. They can be broken up into small particles. Electrons cannot be broken up, but protons and neutrons can actually be broken up even further. Protons are made up of 2 up quarks and 1 down quark. Now quarks, there are 6 different types of quarks. There's up quarks, labeled as U, down quarks, labeled as D. There's strange quarks as S, charm quarks, which is C, top quarks, which are labeled as T, bottom quarks, which is labeled as B. We're going to focus on up and down quarks. Now, they are smaller than protons and neutrons because they make up protons and neutrons. But their mass isn't important for this right now. But basically, an up quark is 2/3 the charge of the elementary charge. It's a positive 2/3 charge, and a down quark is a negative 1/3 charge. So if you want to make a proton, if you make 2 up quarks and 1 down quark, think about the charges. You have a plus 2/3 charge, plus another plus 2/3 charge from each of the up quarks, and then a negative 1/3 charge. 2/3 plus 2/3 minus 1/3 is 1. It's a positive 1 charge, or a positive E charge, I guess you could say. Neutrons are made up of 2 down quarks and 1 up quark. So there's a negative 1, third and a negative 1/3 and a positive 2/3, which makes an overall net charge of 0. So because they're partial charges, it can kind of help to hold those things together. Now, the other quarks kind of go into the other parts of the nucleus, which kind of hold the things together, like the gluons. Within the gluons are also these other particles, like neutrinos and antineutrinos and positrons and gamma particles. So let's go into depth about those. Let me just kind of, since we're not going to focus in on these quarks too much, I'll actually delete this column so it's a little bit easier to see. So neutrinos are basically, their symbol form is this little nu, or looks like a V. They're basically like chargeless electrons. They're electrons, but they don't have any charge. So neutrinos are basically chargeless electrons, and they basically have the same mass as an electron, 9.11 times 10 minus 31. Same lepton number as electrons because they're particles, but the main difference is that they don't have any charge. So they're very hard to detect. The only reason we can detect them is because of their momentum, and they do have like a little bit of impact when they collide with things. There are things called antineutrinos, which is basically a nu or a V with a little dash above it. And basically an antineutrino is the same thing as a neutrino, except when it meets up with a neutrino, it annihilates each other, or they annihilate each other, and they produce energy. But basically it's another massless, or I should say chargeless electron. It behaves just the same as a neutrino, except its lepton number is -1 because when it meets up with the neutrino, they both cease to exist. Now a positron is basically a positively charged electron. It has a negative mass, just like the antineutrino, and it has a positive charge. So instead of a -1 or a negative E charge, it has a positive E. And so basically when a positron and an electron meet up, they annihilate each other because they're the same particle, just anti-pairs of each other. So its lepton number is -1, same as an antineutrino. An alpha particle is just basically a helium nucleus. It's made up of 2 protons and 2 neutrons. They're used a lot in a lot of different detection techniques. So basically the mass is just going to be the mass of 2 protons and 2 neutrons. And the atomic mass unit is about 4 because there's 1, 2, 3, 4 particles. It's going to have a charge of 2e because there's 2 positive charges here. And its lepton number is 1 because it's a particle. A gamma particle is just basically a high energy light radiation particle. And basically it's massless and chargeless. It's just high energy radiation basically. You can think of it like a photon. A photon is a light particle that has basically 0 mass and 0 charge. So hopefully those help, and we're going to use these ideas when we start talking about nuclear reactions. So there are 6 types of nuclear reactions. The first type, this is in kind of random order, but one of the types is alpha decay. And in alpha decay, basically the nucleus emits an alpha particle, which is just a helium nucleus. There's also 2 different types of beta decay. One of them is beta positive and beta negative. One of them releases a positron, that's beta positive, and then beta negative is when it releases an electron. Gamma decay is when a gamma ray or gamma particle is emitted. Nuclear fission is when a nucleus breaks apart into a smaller nuclei. And the nuclear fusion is when 2 nuclei fuse together to form 1. So let's go through the first few together. Now, one thing to consider when writing nuclear reactions is they need to be balanced, just like a chemical reaction. And these 5 things need to be balanced. I put stars next to some of them because I'll come back to those later. The first thing I like to balance are the mass. The mass has to balance on both sides of the equation. The charges have to balance on both sides of the equation. So you can't like gain charge, like you can't have like a +2 charge on one side and a +3 charge on the other side. It has to be +2 and +2, or +3 and +3. The lepton number has to balance, meaning the number of antiparticles and particles have to balance out. Energy, of course, has to balance because conservation of energy, and momentum also balances. Now, the reason this one's starred is because technically there's going to be a little bit of mass that is going to be lost in the reaction, because that mass is converted into energy. And so, but not much. And so we can ignore, when we write the reactions, we can ignore that mass difference until later when we actually start calculating things. But just writing the reactions, we can just assume it's balanced. And momentum also balances, but we don't necessarily need to consider that when we write the reactions. It's just something that is also conserved. Now, why do things actually go through these different types of reactions? Well, it's because they want to become more stable. These nuclei want to become more stable. So every nucleus wants to become iron. So if it's a small nucleus, like hydrogen, helium, lithium, beryllium, etc., all the way up to iron, which is 26, if it's 25 or less, they want to grow. Those nuclei want to grow somehow, become larger, become closer and closer to iron. If they're really big nuclei, especially the bigger ones they are, such as like uranium or gold or platinum or something, they want to eventually break down to become gold because it's more stable. They're too big. They don't want to stick together. So every atom wants to eventually become iron. Now this might take millions upon billions of years to happen, or it might take seconds, depending on how stable the molecule is, or atom is, nucleus is. But basically, when they get to iron, that's when they stop going through nuclear reactions. That's like the death of the reactions. In fact, like stars will start with hydrogen and helium and like fuse together to make bigger and bigger elements. Once they create iron, they die. They start dying out. Now, I kind of redid this table from the last section and kind of simplified it a little bit. Got some just rounded numbers for you. So we have, and also kind of narrowed down the particles too. Protons, neutrons, electrons, neutrinos, antineutrinos, positrons, alpha particles, gamma particles. We're going to focus on those. I just rounded the mass, and we'll use AMU instead of kilograms. So it could be 1 or 0. Alpha particle is 4 because it's made up of 2 neutrons and 2 protons. And instead of writing down the charge in terms of elementary charge or coulombs, I'll just write +1, 0, or -1. Alpha particle will be +2 because there's 2 protons. And lepton numbers, we'll keep it simple. It'll be 1, 0, or -1. So we need to balance these things when we write our reactions. All right, so we're going to start off with this example here. We're going to write the alpha reaction, the beta positive reaction, the beta negative reaction, and the gamma reaction for carbon. So starting with carbon, we're going to write these different reactions. Okay, so what we'll do is we'll start off with carbon. I'll write the symbol for carbon as C. And let's do alpha decay. Now, if carbon goes to alpha decay, it basically is going to produce an alpha particle. Now, an alpha particle is going to be either you can write it as this symbol for alpha, or you can write down He, because basically He is helium. It's going to produce a helium nucleus. That's the same thing. These two are the same. Plus something else. All right, it's going to make something else as well. So let's kind of get some like colors here. I want to write down some numbers. In the lower left-hand side, I'm going to write down the charge, the nuclear charge of each of these things. So the nuclear charge is basically just the number of protons that the object has. So carbon has 6 protons. So the charge of a carbon nucleus is going to be 6. The charge of a helium or alpha particle is going to be 2. Okay, so that means since charge has to be balanced, it's one of the things that has to be balanced, whatever is left over here has to be a 4. Okay, so what I could do is I could say, all right, let's go to 4, and I have to look at my good old periodic table here, and let's see what this says. What element is 4? It's beryllium. Okay, so it's beryllium. So I'm going to write this down, and it'll be beryllium is the particle that's left over. All right, sweet. So now the charges are good. The charge is good. 6 equals 2 plus 4. The charges are balanced out. Now let's look at the mass. The mass is the next thing I want to try to cancel out. I'll do that maybe green. The mass of carbon is going to be 12. And I'll write the mass up here. The mass in terms of AMU. The mass of helium nucleus, or an alpha particle, is going to be 4. So, right over here on this side we have 12, we have 4 on this side, so what plus 4 equals 12? That's going to be 8. It's going to be beryllium 8. All right? So now, going through this, going back to my balance, so I balanced the mass, I balanced the charge. Now I have to balance the lepton number. I have to balance that lepton number. So the way I do that, maybe I'll do that in pink. I'll write the lepton number up here. The lepton number of this is 1, because it's a particle. The lepton number of this is 1. Lepton number of this is 1. So, 1 is on this side. I have 1 plus 1 on this side. I have 2. I have 2 things on this side, so I need something else on this side. I need to add something else on this side, so I need to add something else on this side. And now that's something else that I have to add. It has to have a 0 charge. It has to have a 0 mass. And it has to have a -1 lepton number. Well, I need to figure out what that is. If I look at so 0, 0, -1, I need to look at what that sheet is, and the one that matches up, 0, 0, -1, it's an antineutrino. It's an antineutrino that's conserved. So the thing that I need is an antineutrino. And so I'll put down an antineutrino, and now this is conserved. The charges are conserved. 6 equals 2 plus 4 plus 0. The mass is conserved. 12 equals 4 plus 8 plus 0. And then this is also conserved. 1 equals 1 plus 1 minus 1. Now, energy is also conserved in this. If I wanted to, I could put in plus energy on this side. Plus energy. Because it's going to give off energy. I'll just do nRg. It's going to, and the momentum is also automatically conserved. Now this is my alpha decay reaction. So now let's try the beta decay, the beta positive. All right, so beta positive, if you remember, is one that releases a positron. So let's start with carbon again. And I know that carbon is going to decay into something. Now, for one thing I forgot to mention about the last reaction is you can find these values on the periodic table. The periodic table, you can find the values for all of this, like the charge of the nucleus is just the number of protons, and the mass is usually given for each of the elements too. So you can usually find those on the periodic table, so you don't need to memorize those. But anyway, for beta positive, carbon is going to decay into, well, according to beta positive, it has to produce a positron. Now, if you look back at this, the symbol for a positron is just an E with a positive charge on it, and its mass is 0, its charge is +1, its lepton number is -1. So, let's do that. We have E, a little positive here. Okay, and let me put this in. So carbon's nuclear charge is 6, its mass is 12, and its lepton number is 1. This particle, positron, its charge is 1, its mass is 0, and it's -1 because it's an antiparticle. It's -1 for its lepton number. So now Obviously, this is not balanced. This is not balanced. What I like to do first is balance the charges, or the mass. It doesn't matter. Let's do the charge first. 6 equals 1 plus what? Well, 5. 5 would make that balanced. What I could do now is I can go back to my periodic table and figure out what is 5. Well, 5 is boron. It's boron. So this automatically makes this element boron. Well, boron, what's the mass of boron? Well, I can get that from this. I can get 12 equals 0 plus, well, 12. All right. Now, this I can't change. Boron is a particle, so this needs to be plus 1. Now, this is conserved. The charge is 6 equals 1 plus 5. The mass is conserved. 12 equals 0 plus 12. But the lepton number right now is not. 1 equals negative 1 plus 1. So now I need to add something to conserve this. It needs to have a mass of 0, or sorry, a charge of 0, also a mass of 0, but then a lepton number of positive 1, because this over here is negative 1 and 1, it's 0 and 1, so it needs to have a positive 1. So I can go back to my chart here and try to figure out what this is. I need 0, 0, positive 1, 0, 0, positive 1. That's a neutrino. That's a regular neutrino. A regular neutrino will balance this out. It would also balance out the amount of energy. I could put plus energy if I wanted to. You can always put plus energy on the right-hand side because energy is always going to be released in these reactions, which is why they happen in the first place. You might need to put energy in to start them, but you also get more energy at the end always. So energy is always a product. And momentum is always conserved on both sides as well, which is how we know that these particles, some of these particles exist. But this is a balanced reaction for beta positive. Now, another thing I forgot to mention is this reaction going to happen naturally? And the answer is all these reactions are possible, but some of them are going to be more likely to occur than typical. If a particle gets closer to iron, it's more likely to occur. So in this reaction, carbon is going to boron. It changes to boron. So if I look at this on the periodic table, carbon is here, boron's here. Boron is farther away from iron. Iron's 26, carbon's 6, and boron's 5. Boron is farther away from iron than carbon is. So this reaction that we did is not very likely to occur. It's more likely to occur the other way, where boron would transfer into carbon, but not the other way around. So carbon going to boron is not very likely. Doesn't mean it can't happen, it just means it's not very likely to happen. It's more likely to grow than to shrink. All right, now let's try the beta negative reaction. Starting with carbon, so carbon is going to decay. And now beta negative, going back to that, the definition of beta negative is it releases an electron. So, and it's going to obviously produce other things too. So add a plus there. So we can fill in information with carbon already. We know that the nucleus has a charge of 6 and a mass of 12, and it is a particle, so we got 1. Electron, I'll put a negative here so we know it's an electron, not a positron, has a charge of negative 1 and a mass of 0 and a lepton number of 1. Don't get that negative symbol here confused with that. Now, just start with this. We know it's 6 equals negative 1 plus something. What plus negative 1 equals 6? Well, that's going to be 7. So now I can look at my periodic table and try to figure out what element is 7. That's nitrogen. So nitrogen is going to be my new particle that I create. And then, well, what kind of nitrogen is it? Well, we have 12 here. 12 equals 0 plus 12. So that's conserved. And then this is a particle, so it gets automatic 1 there. But now, if you notice, you've seen a pattern here. 1 is our lepton number over here, equals 1 plus negative 1 to make it balanced out. So now we have 1 plus 1 minus 1. we need something with a, well, everything else is balanced, so this needs to be 0 for the charge, because 6 equals -1 plus 7 plus 0. And then the mass needs to be 0 because this is already balanced for mass. So we need a particle that has a charge of 0, a mass of 0, and a lepton number of -1, and that particle is an antineutrino again. That's the only one that matches. So antineutrino is where it's at. And then obviously you can put plus energy if you wanted to on this side, and momentum is also conserved. Now, is this reaction likely to occur? And the answer is, well, yes, this one is, because if you look at carbon, carbon's 6, nitrogen is 7, and yes, nitrogen is closer to iron than carbon, so this reaction will happen. And in fact, this is the idea of carbon dating. Carbon eventually does decay to nitrogen over time. Now, generally it's carbon-14, not carbon-12 that does this, but doesn't mean that carbon-12 can't do this. So that does happen. And last but not least, let's talk about the gamma decay for carbon. Now, let's start with what we know. Carbon is 6 and 14 and 1. It's going to produce a gamma particle or a gamma ray. Basically, a gamma ray or gamma particle is just a photon. It's a high energy photon, or really high energy light. Now, it is massless, it is chargeless, and it's not really a particle, it's just high energy radiation. So it really has no lepton on it either. So really, this is already, like, I could put plus carbon 6, oh, I put 14 here, carbon 14, it doesn't matter, carbon 12, carbon 14, doesn't matter, and 1, and that would work. This is already balanced. This reaction could work. Is this the only reaction that works for gamma decay? No. Technically, I could add in other things in here too that would work as long as a gamma particle is in here. So I could add in, like, let's say it could be maybe a 0, 0, -1. But then I have to balance it out with a 0, 0, +1. What would these particles be? Well, 0, 0, -1, that is a 0, 0, -1, that's an antineutrino. 0, 0, +1 is a neutrino. So maybe I could put in here an antineutrino and a neutrino. I could even add in, like, a positron, because that's -1. Sorry, it's +1. 0 and -1, and I could add it to something that has a -1 here and a +1 here and a 0. That'd be an electron, and that also conserves. So there's lots of particles I could emit with this, as long as a gamma particle is in the reaction. It is classified as a type of gamma radiation or gamma decay. So gamma decay is basically like any decay that has a gamma ray particle in it. And since this can be really tacked on to anything, because this is really just high energy radiation, you could say that any type of like the alpha radiation that we drew, the plus energy, it could be a gamma ray particle. The beta positive could be a gamma particle. The beta negative, the could release a gamma particle as well. So gamma particles often exist with some of the other reactions. So they're the easiest ones to write, I guess. So our next video that we'll make is going to go over the last two reactions about nuclear fission and nuclear fusion. And we'll also talk about half-life and radioactive dating, like nuclear decay, and talk about that as well. And we'll also talk about energy production using E = mc². And that'll kind of wrap up our nuclear physics content. Energy production, fission, fusion, and half-life, and decay rates. So that's what's coming up in the next video. So hopefully you guys learned some stuff from this one, and have a good day.